Welcome everyone to chemistry class. Solid state. I have already provided you with the readout, so I am assuming you have gone through those definitions, formulas. In this session, we'll try to concentrate more on problem solving. To start with, we all know the general characteristics of solid. That they have definite mass, shape, and volume. And then they, amongst the three states of matter, solid, liquid, and gas, they have the least intermolecular distance, and hence that's why they're rigid. And the solids can be broadly classified into the crystalline and the amorphous, and we'll focus mainly on crystalline solids because they have a pattern of arrangement. Now, when we talk about arrangement of the crystalline solids, we think about the lattice points or lattice systems, and these lattice points are nothing but array of points in space through which we can generate different structures. As you can see, these are points in space which we call as the lattice points, and each lattice point can be an atom or an ion that occupies that particular space in the particular area in space. And by connecting the lattice points in space, we can generate different structures. If we consider only one row, then we can say that's one-dimensional. But suppose if we connect these 4 dots, then we have generated a 2-dimensional structure which looks like a square, or you can even go for a hexagon. Or suppose if we have some more here at this point, then we can even generate a rhomboidal structure. Now, these are 2-dimensional structures because we have 2 sides and an angle. And then if you project this picture or this image into the board or out of the board, then we can generate a 3-dimensional structure. Now, as we know, there are 7 crystal systems, basic crystal systems. Now, as I've mentioned, if we project this into the board or outside of the board, we can generate a 3-dimensional structure such as a cube. Now, this can be called as the unit cell. The unit cell is the simplest entity which, when repeated, generates the whole structure or the whole molecule. Now, this unit cell has, since it's cuboidal, will have 3 different sides, A, B, C, and 3 different angles, alpha, beta, and gamma. Now, whenever we repeat this structure, then it gives you the whole structure when you repeat this unit. Now, there are basically 7 crystal systems. You can see down HRT. So, cubic system, triclinic, orthorhombic, monoclinic, hexagonal, rhombohedral, and triclinic, if I'm not mistaken. Cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, and triclinic. So those are the 7 crystal systems, and this generates the 14 Prevet lattices, or the 14 crystal systems. Now, amongst this crystal system, we have two different types. One is the primitive unit cell, or the simple cubic or simple unit cell, and then we have the non-primitive. So in primitive or simple unit cell, we have only one system. That means a pure cube. But in non-primitive system, we have the body-centered cubic system, face-centered, the hexagonal close packing system, and then we can have the edge or end-centered cubic system. So those depend. They vary because they have different angles. They may have different angles, or will have different edge lengths. I've already presented to you in that readout, so you can go through those things. Now we'll turn our focus to a simple cube. Now, simple cubic system. In simple cubic system, we have we have 8 atoms that occupy the edges. That means these are the lattice points in this cube. Now, if you repeat this structure, then if you project it outside, behind the screen, above, then you generate the whole structure. Now, suppose we want to know how much one atom is contributing to this particular cube. So if we extend it, then you may get a picture. So we can have on top, we can have on the outside. So I'm not particularly good in drawing, so I think you get a picture. So each atom of that particular cube will be attached to 8 cubes, if you can picture it. So the contribution of this atom is just 1/8, because it's this atom, one atom, is sharing with 8 other cubes, and then in this particular cube we have 8 atoms. So if we multiply it with 8, then the contribution is just 1 for simple cubic system. So for simple cubic system, we have only one contribution, or one atom contribution per cube. Now I have redrawn the figure, modified a bit. Now if you look at this edge atom, this from one of the cube, then it is attached to 1, 2, 3, 4, 5, 6 atoms. So if for a simple cubic system, the coordination number, that means the one atom touches 6 other atoms, so coordination number is 6. That's how we find the coordination number for each atom for different cells. Now when we talk about a body-centered cell, it's you imagine a cube, but we have 8 atoms on the edges, but we have one atom at the center. So it's called a body. That's why it's called a body-centered cubic system. So the contribution per atom would be from the edges, we have 1/8 into 8, plus there's one atom in the middle, so contribution per atom is 2. And for face-centered, we have on each faces of the cube we have one atom each. So one at the bottom, you try to imagine. So, and each atom will be contributing half, and then we have 6 of the faces, which means there's 6 atoms, and then we have 8 atoms on the edges, so 1 by 8 into 8, so that gives 4 contributions per atom, and that's how we calculate the contribution of atoms per unit cell. Now let's move on to the density of unit cell. We know by definition that density is mass per unit volume. So for a unit cell, we can say that mass of the total amount or total atoms present in the cell, and then per volume of the unit cell. Now the mass of total atoms, or mass of total atoms should be given by, we know that suppose for simple cubic system, the contribution of atoms is just 1, and the contribution of atoms is denoted by the letter Z, and then that suppose each atom will have different masses. Suppose if it's hydrogen atom, it will be different. Chlorine, carbon, it will have different mass. So molar mass divided by the Avogadro's number will give the mass of that particular element, and then over the volume. And then the volume, since it's a cube, it's suppose if we take the edge, one edge as A, then it will be A cubed. So the density is Z into M over A cubed Na, and this Na is our Avogadro's number, and A is nothing but our Avogadro's number. So that's how, this is an important formula for calculating the density of a unit cell. Now we can even calculate, we can even look at the packing efficiency. Suppose how closely the atoms are packed in a unit cell. Suppose for simple unit cell, it will be different because the contribution is only 1 per atom. For body-centered, contribution is 2, so it will have a different packing efficiency. For face-centered, it's different. For hexagonal cubic system, it's different. So packing efficiency is given by volume of atoms in a unit cell, volume of atoms in unit cell over the total volume of unit cell, the total volume of unit cell into 100. That gives us the packing efficiency. It's in percentage. Now talking about different types of packing, we can have these 2 different types of packing. This is called the square packing system, and this one is our hexagonal packing system. Now this, in square packing system, all the atoms are stacked, the layers are uniform, stacked on top of each other, and hence they are loosely packed compared to hexagonal packing. In hexagonal packing, this is called A type because all are similarly packed, but this one is A type, the hexagonal. Now the first layer, between the first and the third layer, in between the atoms coincide, and hence we get the hexagonal type of packing system. In square type of packing, we can get our simple cubic system like this, or we can have we can generate this way also, a body-centered cubic system. But in hexagonal packing system, we can have a rhombohedral type or the regular hexagon type packing system. So as you can see, if you can picture it, so and hence the packing system is also different for different types of crystal systems. Now we'll try to establish the packing efficiency of different crystal system for simple cubic body cubic system and for hexagonal or face centered. Now for calculation of packing efficiency for simple cubic structure, let's picture this as a three-dimensional simple cubic system. Now if we consider the atoms as spheres, so this from the center of one of the sphere to the other center will be the length of each sides. So if we take this as A, then A would be nothing but, if we consider this as a sphere, then it will be the radius, so twice R. So one edge would be twice of the radius. And we know that the contribution per atom is, in a simple cubic system, is 1. So the packing efficiency, as we know, packing efficiency is equal to volume of the atoms in a unit cell. So volume of the atoms in a unit cell is Z into, since the volume of a sphere, as we know, is 4 by 3 pi r cubed, over the volume of the edge, or the volume of the cube, so it's edge length, so it's twice r, the whole cube. Now Z is 1 into 4 by 3 pi r cubed over 8 r cubed. So if you calculate, then you'll get 0.5233. So if you multiply it with 100, then we'll get 52.33%. That is the packing efficiency of a body-centered cubic system. Sorry, the previous calculation was for simple cubic system. Now we'll try to calculate the packing efficiency of the body cubic system. Now for body-centered cubic system, we'll have one atom at the center. My drawing is not that accurate, so you just try to get a picture of what I'm trying to say. And in body-centered cubic system, the edge atoms are not touching, so we cannot use like the simple cubic system, the edge where the edge was twice of the radius, we cannot use it. So for calculating the edge length of a body-centered cubic system, then we need to use Pythagoras theorem. So by applying Pythagoras theorem, you will arrive that the sides is equal to root over 4 or root over 3 by 2. You can arrive at 4 by root over 3 r. That would be the edge length for body cubic system. Now if you plug in those packing efficiency in the equation, then for body centered we have calculated the contribution of atom to be 2, and then 4 by 3 by r cubed over the edge length r cubed. So if you calculate, if you minimize, then you'll arrive at 68%, the packing efficiency. Now you can try for face centered in a similar way, and then for hexagonal close packing system. This is a bit tricky. If you can leave a comment, or you have my number, so you can contact if you have difficulty in solving. So here is a problem. Potassium crystallizes in body centered cubic lattice. So with a unit length A 5.2 angstrom, so you are asked to calculate all these 5. What is the distance between nearest neighbor and all. Now you can pause the video, you can solve on your own. In a short while I'll give you the solution. For part A, we know that the distance between the nearest neighbor for a body-centered cubic system is given by root 3 by 2 into A, and they have already given us the distance. So root 3 by 2 into 5.2 angstrom will give us 4.5 angstrom. That is the first answer. And for B, the what is the distance between the next nearest neighbor? So this is the next nearest neighbor, so answer is 5.2 angstrom. For C, how many nearest neighbors does potassium atom have? Now that means the coordination number, and for body-centered cubic system the coordination number is 8, so the answer is 8. For D, how many next nearest neighbors? Sorry, these next nearest neighbors does each potassium atom have? So in that body-centered cubic system, so this is the body-centered cubic system, so each potassium atom will have how many neighbors? So see, then if we extend it, then we'll have this atom will have 1 2 3 4 5 1 2 3 4 5 and 6. So the answer is 6. And for the last, that is the calculation of density. Now the density is Z into M over Na into A cube. So everything is given. This one, you know, for body center it's 2, and the molar mass of potassium is 39, sorry, 39. Then the edge length is given as 5.2 angstrom, and into 10 raised to the power negative 10 meters, I think, into Avogadro's number 6.022 in the 10 raised to the power 23. So this is whole cubed. So if you calculate, you'll get around 0.92 grams per centimeter cubed. So that's how you can calculate the density. Yeah, you can try these 2 problems. If you have any queries, you can contact me, and then we'll do another session for this chapter.